Okay, so we'll end the first notes here with a couple examples, hopefully help illustrate everything pretty well. Okay, so particle moves along the x-axis. Its position varies with time according to an expression x equals negative 4t plus 2t squared, where x is in meters and t is in seconds. Okay, so do notice that we're in our standard units. Make sure you are paying attention to those because those could maybe make this a little bit trickier. But you're going to see a lot more of these here. You're going to see a lot more where they give us functions and equations and relationships that describe the position, because now we can do calculus, so now we can find derivatives and integrals, which we'll talk about later as well. But you can do a lot more with these now. Okay, so part A, however, not terribly difficult, right? Determine the displacement of a particle in the time intervals from t equals 0 to t equals 1 and t equals 1 to t equals 3. Notice the nice thing that they say here is the displacement and not the total distance traveled. So I don't care if it's gone up and back or whatever within that time interval. I just want to know where was it at time t equals 0 and where was it at time t equals 1. And right, if they give me the position function, I simply plug in these values. So at t equals 0, I plug in 0 and we started at x equals 0. At t equals 1, I plug in 1, so negative 4 times 1 plus 2 times 1 squared. So at that location, I was at negative 2. So my displacement from 0 to 1, if I want to call that delta x from 0 to 1, or however you want to designate that, was negative 2 meters, right? And do make sure, again, we're following our units, but negative 2 meters there. Then from 1 to 3, well, I already know at 1 it was at negative 2 meters, so I just have to figure out at 3. So when I plug in 3, I get negative 12. When I plug in 3 squared, 9 times 2 plus 18. So I end up getting positive 6. So my displacement from 1 second to 3 seconds, I started at negative 2 meters and then I went to positive 6 meters. So that was a displacement of positive 8, right? So my delta x is from 1 to 3 is positive 8. Anyway, so I've got that set up for me. Part B, calculate the average velocity during these two time intervals. So the average velocity, right? Average velocity, because it's just the average, is my change in displacement over time. So now that I know the displacements for both of those, that's not really too big of a challenge, right? I'll go ahead and work that down where I have a little bit more space. I gave myself all this space, I might as well use it. So for 0 to 1 second, right, from 0 to 1 second, if I want to find my average velocity, and notice I am going to use that line above it to designate average, I'm finding my change in displacement, which I know is negative 2 meters, and the time, which would just be 1 second. So my average velocity from 0 to 1, again, however you want to designate that, negative 2 meters per second. From 1 to 3 seconds, my average velocity, again, I already found my displacement was 8. My time, right, my change in time was 2 seconds, so my average velocity was positive 4 meters per second. And by the way, it is worth mentioning, again, you'll have a lot more in the way of calculations for this AP test. So hopefully, if you are looking at taking that at the end of the year, if you had messed up Part A but used it correctly for Part B, you're fine, right? You get full credit for Part B, you just miss a point or two on Part A. But anyway, Part C is where we actually get to have a little bit of fun, right? Parts A and B were really stuff we did last year. Part C is the only thing that's new this year. Find the instantaneous velocity of the particle specifically at 2.5 seconds. Okay, so really if you had the graph of this, if you made your graph, you could sketch out your graph. You know it'd be a parabola of some kind, right, because it's got the x squared. So you could sketch your graph and then start just finding the slope at very, very small intervals. But instead of that, right, what we're really doing is we're finding the derivative of that function, and then that's our velocity. Okay, so again, I'm starting with a position function that's negative 4t plus 2t squared. Just let me double check to confirm, make sure, yep, negative 4t plus 2t squared. If I find the derivative of this function, that will represent my velocity with respect to time. Okay, so if I find the derivative with respect to time, so dx dt, if you will, that will find then my velocity function. So using the power rule, well, I bring the 1 out front, I get a negative 4. I bring the 2 out front here, that'd be 4, and then t to the first power. Okay. So again, hopefully you're comfortable with power rule. If you're not, let me know, but I think you guys probably are. So this is nice because this gives me the equation that represents my velocity. So now I can find the velocity at any given time by just using this function, using this equation. So if they ask me for 2.5 seconds, if I want to find the velocity at 2.5 seconds, I'm just going to plug in 2.5. So -4 plus 4 times 2.5. I use half of my 5 rule, right? So half of half. Anyway, 2.5 times 4 is 10, so I get 6, right? So my velocity, positive 6 meters per second at that location. And kind of pause for a second to make sure that makes sense. I know that the average velocity from 1 to 3 seconds was only 4 meters per second, but at 1 second, didn't we actually start with a negative velocity? So by the time we're towards the end of that interval, we're going to have to be in the positive range to balance that back out and give me an average of 4. But in any case, I hope that this process isn't too bad. So my velocity at 2.5 seconds is 6 meters per second, is positive 6 meters per second. I should include both positive and the units. A little foreshadowing here. I'm sure most of you guys could probably make this conclusion anyway. Probably not Kenny, but maybe Ashley and Nathan would be fine on this. But anyway, if you do the derivative of the velocity, what are you going to get? And Harding's probably already talked about it in calc, maybe. But if you do the derivative of this, you're just going to get your acceleration function. So if I do the derivative one more time, this guy would go away, this guy would go away as well, and I would just be left with 4. So that actually tells me that the original context up there has a constant acceleration of 4 meters per second squared. We will talk more about this in the future sections. Like I said, this was just a little bit of foreshadowing. Example 4, very similar, right? Very similar. So particle's position is given by the function x equals negative t to the third power plus 3t. It is in meters and t is in seconds. What is the particle's position and velocity at t equals 2 seconds? Okay, again, don't ever overthink the position questions, right? If I want to find the position and it gives me the function of x, I just plug it in. Right, so I plug in 2, so for part A here, the position at 2 seconds, I'm just plugging in 2, so -8, and then plus 6, I get -2 meters. I know I didn't show my work, but I hope you guys could follow that okay. For my velocity at 2 seconds, it is indicating a specific time, so I'm looking for the instantaneous velocity at that point, so I'm going to find my derivative, right? -3t squared plus 3. That's the derivative of this function using the power rule. And just bringing that out front, reducing by 1, bringing 1 out front, reducing to make the t go away. Okay, so once again, plug in 2. So I have -3, I'll show work this time, times 2 squared plus 3. So -12 plus 3 would give me -9. So the velocity at 2 seconds is -9 meters per second. Okay, so hopefully that part wasn't too bad. Draw graphs of x and v of x during the interval from -3s to positive 3s. I don't know that I'll necessarily work this all the way out, but what I will say is you can use your calculators, right? So the whole point of this now is you can use your calculators. You've got an equation. So to draw your graph for x, right? So if I want to do my position versus time graph, I know that's probably not giving me the range I actually need, but I'm just ballparking it here. Okay, so for my position versus time graph, I'm going to plug this function into my graphing function in the calculator. So I can literally plot whatever points I want. So from -3 to 3, I can just calculate those values and plot those points. You can do the exact same thing, for v and t. So plotting this, this equation in there, and then plotting the points from -3 to 3. Like I said, I don't think I'll take the time to do this because that would probably make this part way too long. So I will trust that you guys maybe practice this and make sure you do feel comfortable with it. But again, all you're doing is using a graphing calculator or a table of information or whatever you want to do to plot those two different graphs. You're just graphing the functions like you've done for several years now. So anyway, the big moral of the story is you can graph these functions even though they're not going to be straight lines. And we'll look at that more as we go throughout the year. So then the last example, just a quick matching example to make sure we're feeling pretty comfortable with all of the graphical interpretations, right? So which velocity versus time graph goes with the position versus time graph on the left? Well, if we start here, and notice they use S instead of X, but our textbook does that. The AP test still tends to use X for the most part, but they may use S every once in a while as well. But anyway, so we're starting with the position versus time. So if I want to find the velocity on this graph, I'm looking at the slope, right? Well, the slope for the first stage of this graph is definitely positive. Now it gets less and less positive as I go, but it's definitely positive, right? By the end of this, the slope is about 0. Okay, so if I'm looking at this, the velocity was never negative. The slope was never negative. So that doesn't make any sense, and option D doesn't make any sense. So then we're down to B and C. Don't be fooled by B. Yes, our position is going in the more positive direction, but our slope and therefore our velocity shouldn't be increasing, right? Our slope is decreasing over time, so the velocity graph should not be getting higher, right? I'm not looking at the slope of this graph, I'm just looking at the actual points, right? These points continue to get higher and higher and higher. The slope is not increasing. That doesn't work. Instead, the velocity was fairly constant for the first couple seconds here, so fairly constant velocity, but then at some point we start to slow down until eventually we reach 0. Okay, so option C is definitely our best answer with that one. Okay, so this finishes the first section of the notes. Hopefully this helped you out. Hopefully it wasn't too much of a waste of time, but give me some feedback on it, and we'll see if this helps moving forward.